So good afternoon. Let us start our lecture today. So in the previous class, we was trying to prove the risk theorem. Right. So what is the risk theorem? The risk theorem said that if you have one smaller than infinity and smaller than bigger than one, then suppose that L is in LP prime star, P prime is the dual of P, then there exists a unique function U in LP such that L of F will be equal to UF for all of the F in LP prime. All right. So we know from the previous proof that so we already know that for V in LP, for all of the function V in LP, I can define a TV of F of the form VF, right? For F in LP prime. And in this case, the norm of LV, TV will be the same with the norm of V in LP. This is why we can consider LP as a closed subvector space of LP prime star. All right. So this is LP, and this is the map T, right? And this is LP prime star. So this is V, and this is TV, right? So we know from the previous proof of the fact that LP is reflexive that you can define this operator for any V from LP. So this operator maps all of the V in LP into a TV which is in LP prime star, and this TV is defined in the following way. So TV of F will be the interval of VF for all of the F in LP prime, right? So we also show that the norm of this mapping of this linear operator is the same with V. So this is why we can consider LP as a subspace, a closed subspace of LP prime star, right? So now we want to show that indeed this LP will be the same with LP prime star, right? So we suggested a strategy. So we said that okay, LP will be this vector space B, and LP prime star will be this vector space B, right? To show that A and B are the same, we will consider an operator, a linear operator, I call it H in B star, right? And if H of V will be 0 for all of the V in A, implies that H is 0, then A and B are the same, right? So this is the strategy that we discussed before, right? So to show that A and B are the same, we will consider a linear operator H in B star, such that if HV is 0 for all V in A implies that H is 0, then A is the same with B, right? Otherwise, if A is not the same with B, we're gonna consider a vector which is in B and not in A, and we consider H to be the projection of a vector onto that dimension, and then this is not 0, all right? So this is where we stopped last time, all right? So we're gonna apply this strategy. Right, so we show that, okay, we show that any H in LP prime star star and H of V is 0 for all of the V in A, implies that S is 0, right? So this is 1. Right, so I recall, so LP will be A and LP prime star will be B. All right, so we're gonna prove that if H is in B star and H of V is going to be 0 for all of the V in A or P, then H has to be 0. All right, it's good. So this is what we have to prove, right? So now this is what we need to prove, right? And if we can prove this, then A and B are the same. If this is true, then LP will be the same with LP prime star. All right. So we're gonna have to prove that if we pick an H in B star, and if this H of any V, where V is in A or LP, then H of V is 0, and this implies that H has to be 0. And if this is true, then A and B are the same, or LP will be LP prime star, right? Now, so I pick H in B star. All right. What can I say about H? Right. So H is in B star. So now, what is B star? B star will be LP prime star, right? So what can I say about H? What can I say about LP prime star? No? What is LP prime star? What is the dual of the dual of LP prime? No?
LP prime.
Right. Stephen got it correct. So the LP prime star will be LP prime, right? Since LP prime is reflexive, right? So this is by Stephen, right? Right. So you know that, okay, H is in B star, which means that H will be in LP prime star. But LP prime is reflexive because P, all of the LP will be reflexive for P is going from 1 to infinity, and because P is from 1 to infinity, P prime is also from 1 to infinity, which means that LP prime is also reflexive, right? This is because 1 is smaller than P prime, and this is smaller than infinity. So in this case, you have L is in LP prime, right? And now suppose that H of V is 0 for all of the V in A, meaning that H times V dx RD will be 0 for all of the V in LP, right? So for this H in LP prime, I say that the effect of H on V will be 0 for all of the V in LP, right? Which mean that the integral on RD of H times V dx is 0 for all of the V in LP, right? So I reduce the problem into the following. So we have one H in LP prime, and the integral of H V dx is going to be 0 for all of the V in LP prime. Can we say that S is going to be 0? So I have a very simple questions. I have that H is in LP prime, and I have that H times V and I take the integral. Then this has to be 0 for all of the V in LP, right? Can we say that this S is 0? Right, so I explain again. So we apply the previous strategy, right?
I think so.
Yes?
I was going to say, yeah, I think so, because, I mean, otherwise all of the V in LP would have to be 0 for the integral to be 0, right? So then it must be 0.
Right. So Stephen got it correctly. So S has to be 0, but we have, yes, yes, Tyler also got it. So, but how can I show that S is 0? Right? So we're gonna, well, it is similar to holder, but this is not holder. This is something that we used in the previous class, right? So in the previous class, we showed the norm of a linear vector space, of a linear operator is bigger than the norm. So in the previous class, right? Remember that we consider TU of f to be this integral on RD of u times f, right? U is in LP, right? So how can I pick up the value
right.
of
So we showed,
yes,
we showed that that was equal to the norm of u, and if we're saying that this bilinear form is equal to 0, then the norm of u has to be equal to 0, but u is h in this case. And by the property of norms, that means that h is identically 0, right?
can you repeat? Can you repeat it?
Yeah, so if you, what you just wrote, if you replace u with h, then that means that the norm, that this bilinear form, right? So this norm is equal to u, but we're saying that this t of u is equal to 0, so that means that the norm h is equal to 0, but that implies that h is identically 0.
Right. So this is basically the point, right? So in this form, in the previous class, I chose a special form of f, right? So that the ratio between TU, f between the norm of f will be the norm of u, right? So we're gonna use similar thing here because I'm gonna replace u by h, right? Like what Stephen said, right? Stephen idea. So then in this case, th of f over the norm of h, the norm of f in LP prime. So we have strict p parametry, right? So this is gonna be p, and this is going to be the norm of h in LP prime, right? And because this is 0 for all of the v or f, then this has to be 0, right? So what is the f that I chose? What is the form of the f? You remember what is the form of the f? So in the previous class,
Norm of v?
no. So in the previous class, I chose a special form of f, so that this ratio become the norm of u. Of course, here I have to switch between p prime and p, but this doesn't matter. So what is the form of f? Right? So in the previous class, what I chose was f is equal to u to the p minus 2 u. Right? Remember that? So in the previous class, I chose f to be u to the power p minus 2u, right? Then because u is in LP, then f is an LP prime, right? And then tu of f will be the integral RD of u p to power minus 2 uu dx, and this is going to be RD u to the p dx, right? And this is the norm of u. Remember that? So this is how I prove that the norm of TU will be the norm of U, right? Now we're going to use kind of the same thing. Let us try to write this idea in a, yes, Surab got it right. All right, so Surab did that correctly, right? So now, so you have what? You have RD of V dx will be 0. So yes, Surab got it correctly. So now you have what? You have, this is okay. This is 0 for all of the V in LP, right? So because H is in LP prime, I'm not using the P, I have to use the P prime, right? Right, so so then I'm gonna choose V to be H to the P prime minus 2 times H, right? And this is going to be in LP, right? So because H is in LP prime, then V is H P prime minus 2 times H is going to be in LP. Why? Because V, the absolute value of P will be H to the power P prime minus 1, and V to the P will be H P prime minus 1 times P will be P prime over P prime minus 1, and this is H P prime. All right? Right, so remember here I have P is P prime over P prime minus 1. Right? So let me rewrite here. So I have what? I have the integral ID of H V dx is going to 0 for all of the V in LP, right? So now I have H is in LP prime, all right? So now I choose V to be HP prime minus 2 times H, exactly like in the previous strategy that we did. So what happened now? So what happened now is the absolute value of V will be H P prime minus 1, and V to the P will be H P prime minus 1 times P prime minus 1, because in this case P will be P prime over P prime minus 1, and this gives me H P prime, right? So which means that integral of H P prime dx 1 P prime will be integral of P dx 1 over P prime, and this is okay. This is very fine. So H will be in LP prime. All right. Sorry. V will be in LP. Sorry. V will be in LP. So this is 1 over LP. This is 1 over LP. Right. So V will be in LP, which means that I can put it here. Right. So now I'm gonna have what? H V dx will be 0 by definition, right? By this property, which means that I have integral ID of H times H P prime minus 2 times H, right? So, and this is going to give me integral ID of H P prime dx, and this integral has to be 0. And H, the absolute value of H is positive, so which means that H has to be 0 almost everywhere, right? It's clear? I explain again.
Yes.
I have that H V dx is going to be 0 for all of the V in LP, right? So H is in LP prime. So I can choose V to be H P prime minus 2 times H, right? So this is the kind of thing. This is a trick. This is a very nice trick, but we have to remember this trick, right? And there is no so it's just a trick, and we have to keep it in mind because it's beautiful and it's gonna help us for many proofs, right? So now you're gonna have what? You have that V to power P will be H P prime minus 1 P prime over P prime minus 1, and this is H to power P prime. All right. So which means that V will be in LP because H is in LP prime, right? So this choice will give you a function V in LP. Now you multiply this here, what do you get? You get that, okay, HV dx is going to be P prime minus 2H, right? And this is going to be the integral quantity of HP prime dx. But this is a positive quantity, and this is going to be 0, meaning that H has to be 0, right? So the trick here is the following. So to summarize all of the proof, the trick is simple. The trick will be, if F is in LP, you're gonna have to remember that FP minus 2F is in LP prime. That's it. If F is in LP prime, of course, you have to replace P prime with P. Right, so this is a nice trick, and we have to keep this in mind, or because it helps us a lot, right? So basically, what did we prove? We proved that, okay, so if H is in LP prime, and come back to the previous computation. So if H is in LP prime, and if the integral on RD of HV dx is going to be 0 for all of the x, for all of the v in LP, then H has to be 0, right? Which means that this is true. And because this is true, then LP has to be identically the same with LP prime star. All right? And because LP is identically the same with LP prime star, the Risk theorem is proved, meaning L is a linear operator in LP prime star, then there should be a unique U in LP such that L of F can be presented as the integral of U times F for all of the F in LP prime, right? Any questions? So let me explain this again, so that you get the idea of the Risk theorem. So what is the Risk theorem? The Risk theorem say the following. The Risk theorem say that if I pick a linear operator on LP prime, right? So this linear operator will be acting on all of the function f in LP prime, right? So there is only one unique presentation of this linear operator on LP prime, which is of this form, right? This linear operator has to be the integral quantity of some function u times f dx. This is the only form for all of the linear operator on LP prime, and this is very surprising, right? So all of the linear operator on LP prime has one unique one unique form, which is of this form, right? So why is it? So in the previous proof, we know that, okay, LP is a closed subset of LP prime star, right? And we want to show that, so LP is a closed subset of LP prime star. So we want to show that LP and LP prime star has to be the same. Why? Because in the previous class, we show that LP is a closed subset, a closed vector space of LP prime star in the following way. So you pick all of the V in LP, and you define the linear operator by integrating the V with all of the F in LP prime. So to show, but basically the Risk theorem said that this is the only form that we have, right? So you integrate one U in LP with all of the F in LP prime, and this is the unique form of all of the linear operator. So we show that, okay, if we pick V in LP and we define this operator, then we form, we can embed LP to be a subset of LP prime star, and we want to show that, okay, and we want to show that this way of doing defining the linear operator is identically the same with the space of all of the linear operator on LP prime star. In other words, we have to show that LP has to be the same with LP prime star, right? Any questions? It's good, right? So now to show that these two spaces are the same, I'm gonna prove that. So there's a strategy that we discussed in the previous class, which is which says that if I pick any linear operator in B star, and if I add this operator on all of V in A, and if H has to be 0, then the two space A and B will be the same. And this is how we prove it, right? So now I'm gonna pick an H in B star. So A will be LP and B will be LP prime star. So you remember that A is a closed subvector space of B, right? So now if H is in B star and SV is 0 for all of the V in A, which is LP, then H has to be 0. And if I can prove this, I can prove that LP and LP prime star is the same. And if LP and LP prime star is the same, this representation will map all of the LP into all of the LP prime star, which means that this theorem is true. All right. Now, how do I prove this thing? So the idea is very simple. The idea is the following. I'm going to pick an H in B star. All right. I'm going to pick an H in B star. And this B star will be what? Will be LP prime star star. So LP prime is reflexive, meaning that this B star has to be an LP prime. So H will be in LP prime. Right? So H is in LP prime and S, so which means that because H of V is going to be 0 for all of the V in LP, meaning that I have that the integral of S times V dx is going to be 0 for all of V in LP, right? So the problem becomes a very simple problem. So if we have H in LP prime and the integral ID of HV dx is going to be 0, then for all of the V in LP, then can we say that H is 0? Yes. Why? Because we have a very simple trick. We say the following. So if F is in LP, then F P minus 2 F is in LP prime, and F is in LP prime, and F P minus 2 F is in LP, right? So now I have H V dx is 0 for all of that V in LP. So you know that H is in LP prime. Then we can choose V to be HP prime minus 2H, right? Which is here. So this V has to be in LP. So you plug this V into this expression, you get HP prime minus 2H, which is HP prime, meaning that H has to be 0 almost everywhere. So we prove the Riesz theorem. It's clear? Any questions? All right, so if there's no questions, we will move to the last theorem of our course, and after, which is the Laxman. And after doing the Laxman, I'm gonna show you one application of Laxman in finite element method. All right?
I have a question.
Yes?
Do we need to prove the uniqueness?
The uniqueness of what?
Of the U.
Okay. Yes, this is a very good questions. So Liu asked a very good questions, right? So yes, so yes, so we have just show that, okay, okay, this is a good question. So we have just show that, okay, so this LP and this LP prime star is the same, right? So in other words, if I have a linear map in LP prime, there is a unique U in LP such that L of F is UF dx, right? Right. So what did we show? Right. We have shown that, okay, very good questions. For all of the L in LP prime star, there exists a U such that L of F is going to be the integral ID of U F dx for all of the F in LP prime, right? So is the U unique? So this is few excellent questions. right? So we've just showed that, okay, because LP prime star is the same with LP, right? Which means that for all of the L in LP prime star, I can map it back to LP in this form, right? So I can map it back like the inner product of U and F, and I'm gonna integrate them on ID, right? So of course we show that there is U, but is the U unique? Anyone? This is an excellent question. So my question is that what? Of course, this is unique, right? Because the theorem said that this is unique, but why? To see why, all right. So suppose that you have U. Suppose that there are two U and U prime, such that U times F dx is going to be L of F, and L of F is also U prime F dx, right? For all of the F in LP prime. Can we say that U and U prime, they're the same?
Yes, almost surely.
Why?
The same idea that prove the two space are the same.
Right. So you're gonna right. So Liu's answer is also very good. So you're gonna suppose that they're the same, right?
Mm-hmm.
So then you're gonna have U F dx is gonna be the same with U prime F dx, right? So I subtract the two. So when I subtract the two, I have U minus U prime F dx is going to be 0, right? For all of the F in FP prime, right? So now I'm gonna choose, because U minus U prime is in LP, then U minus U prime to the power P minus 2, U minus U prime is in LP prime. All right, so it's the same idea. So which means that I can choose this to be F, right? So then I have U minus U prime P to power minus 2, U minus U prime dx is going to be 0, which means that U minus U prime P dx is 0, meaning that U and U prime, they're the same. Right. I explain again. So we indeed, so Liu asked a very good point. So from the previous proof, we know that, okay, you have L of U will be the integral idea of U F dx for all of the F in U L prime, right? So for all of the L, there is a U. But is this function U unique? Yes, it has to be unique. Why? Because we can prove, we can have a proof by contradiction, right? So you suppose that there are two functions U and U prime, so that this L of F can be expressed via U and U prime. So L of F will be the integral of U F dx and also the integral of U prime F dx. And we'll have to prove that U and U prime are the same, right? So why are they the same? Because they're the same, because these two integrals are the same with L F, so you can subtract them. Then you're going to have U minus U prime F dx is going to be 0 for all of the F in LP prime, right? So U minus U prime is in LP, meaning that U minus U prime P minus 2 U minus U prime is in LP prime. I call it F. Right? So I can choose this to be F, and I plug it back to this F. So it's exactly the same idea that we've just used. And this is a trick which is very powerful trick. So when I plug F back into this form, I'm going to have U minus U prime P minus 2 U minus U prime dx is 0, which means that U minus U prime P dx is 0, which means that U is equal to U prime almost everywhere, right? Right? It's clear? Right. So basically, Now we finish the risk representation theorem, and we go to the last thing that the last theorem, and after that we're gonna go through some application in finite element method, right? Using Laxman theorem. So this is the theorem by Laxman. And this is basically the key technique that you use to show that an elliptic equation has a solution. So what is the Laxman theorem? So suppose that S is a Hilbert space, right? And because of the Hilbert space, you have a norm, and then you also have an inner product, right? So H will have an inner product and a norm, right? So now suppose that B is going from S times S to R, and this is bilinear. And also this is first you're gonna have boundedness or continuity. So right, so the boundedness and continuity of this says the following. So B of UV is going to be smaller than an alpha U, the norm of U times the norm of V, right? So alpha is a strictly positive constant, right? So so H is a Hilbert space, and this is a bilinear form in the sense that this is linear in U and this is also linear in V, right? So this is bounded in the sense that if you take the absolute value of this B, which is, then you're going to have that the absolute value of BUV is going to be smaller than the norm of U times the norm of V, up to some constant alpha, which is positive, right? So number 2, coexivity. So this is, there exists a beta which is strictly bigger than 0. This is a constant as well, such that you have B of UU is going to be bigger than B U square, right? For all of the U in H. And this is for all of the UV in H, right? So suppose that L is bounded and linear mapping. L is going from H to R, right? So then there exists a unique U in H such that V UV will be L of V for all of the V in H, right? So basically this is how you solve an equation. You can write the equation in terms of a bilinear form, and the left hand side you write it in terms of a linear mapping. So what you have, so V in this case will be the test function, and U will be the solution of that you are looking for, right? So I repeat, so you consider a bilinear mapping, which is of this form B of UV, right? So this is a bilinear mapping because it is, if you fix V, it is linear in U, and if you fix U, it is linear in V, right? So this is how we define a bilinear mapping. This mapping has two variables U and V. If you fix V, then this is linear in U, and if you fix U, this is linear in V. All right. Now, if this guy is bounded in the sense that if you take the absolute value of BUV for any U and V, then this is smaller than the norm of U times the norm of V up to some constant alpha, which is strictly positive. This bilinear form is also coexistent in the sense that if you put V to be equal to U, right? So in this case, you have BUU. So the BUU will be bigger than the norm of U square for all of the U in H. And this is up to some constant beta, which is fixed. Now, so this is the left-hand side, which is this B. And on the right-hand side, you have what? On the right-hand side, you have this L, right? So this L is a bounded linear mapping on from H to R, right? So which means that if you pick any V in H, L of V is linear in V, and this is bounded in the sense that you have the norm of L of V will be smaller than a constant C times V, right? So this is how you say that this linear mapping is bounded, meaning that the absolute value of L of V is going to be smaller than the norm of V, right? So then there is a unique U in V in H such that B UV is L of U, L of V for all of the V in H, right? So I recall you that, okay, so what is the application of this kind of theorem? So the application, for instance, we want to show this equation, right? So if F is something in L2, so how do we do it? We multiply. So recall. So this is basically a linear analytic equation, right? So we want to show, we want to find a U such that minus Laplacian of U plus U is equal to F. So how do we do it? So we're going to multiply that with a stats function. So after proving this theorem, I'm going to go deeper into the application of Laxman-Graham theorem, and then some of the basic concept of finite element method, so that you are motivated with the real application of Laxman-Graham rather than just the functional analysis aspects, right? So phi will be a test function. Say phi will be an L2 for all of the test function, right? So you want to show this, to solve this elliptic equation, you multiply both sides of the equation with the test function. So now this is by the Green theorem. Suppose that this is on D. So by the Green theorem, or by integration by pi, I'm gonna turn this into Nabla U times Nabla phi, right? And this is still U phi, and this is F phi, right? So this is basically the bilinear form U phi, right? And this is L of phi. And if you can show that this is bounded, of course it's bounded. If this is bilinear and boundedness, this is a bilinear, bounded bilinear form, and if you can show that this is coexistent, then this has to have a unique solution U, right? So here I wrote it V, so maybe I change this into V. So the test function will be V. Right? So I multiply both sides with the test function V. So the first term, by integration by pi, I turn it into the nabla of U times the nabla of V. The second term I keep it, which is U times V. The last term will be F times V, right? So this is going to be this bounded linear mapping from H to R, right? And the left hand side will be our B, which is the bounded bilinear form, which is also coexistent. So then there has to be a unique U such that B of UV is equal to L of V, right? U and U is unique. There exists a unique U such that B of UV is L of V, right? It's clear? Any questions? Right? So we're gonna, you don't worry about this because we're gonna I'm gonna give you all of the setting for the functional space for elliptic equation after we prove the Laxman graph theorem, and after that I'm gonna go into finite element method, some very basic concept of finite element method after proving the Laxman graph theorem, right? So let us go to the proof of the Laxman graph theorem. So basically, the proof of the Laxman graph theorem is in chapter 5 of Brezis. But the proof is very complicated because this is based on Stampakia theorem. So now what I am going to do is to give you a much shorter and nicer proof for this Laxman graph theorem. But you can keep reading Brezis because this is so nice. But at least you know a shorter way to show it. All right. So now, for the sake of simplicity, we consider H to be L2 of RD, right? Say, because but the proof should be true for any Hilbert space. But let us focus on the L2, a special case in which the Hilbert space is L2 RD. And once you know this proof, you can extend it to all of the Hilbert spaces that you know of. All right. So for the sake of simplicity, I'm gonna show you only the special case in which S is L2 of RD. All right. Now, so step number 1. So consider fix U in H, which is L2 of RD, right? And now we look at the mapping. V to B of UV. What can we say? Right? So now suppose that I fix U in H, which is L2, and we look at the mapping, which is going from V to B UV. What can we say about this mapping? Suppose that U is fixed. Can anyone tell me what is the property of this mapping? No? So remember that B is bilinear. So what is it? What is the mapping of from B to BUV? So B is bilinear, right? So if I fix V and I consider only the mapping in V, what do I get? So you remember what is the definition of a bilinear map? Product of the norm up to a constant which is bounded, right? So not yet. So if you consider absolute value of UV, then this is smaller than the product of the norms, right? Absolute constant. So what one property is that if you consider absolute value, right? So this is smaller than the product of the norm up to constant. Yes. This is one thing that you can deduce. This is the first thing. But what is the simpler thing? So can you remind me what is the definition of the bilinear form? Surab, yes. So Surab answer is correct, right? So B is linear in both U and V. So now if I fix U, what is it? Right? So, right, Abdullah's correct, right? So this is correct, right? So Surab. So Surab said that B is linear in both U and V. So, and then when we fix U, then V, BUV is linear in V, right? So this is Abdul, right? So basically this is nothing but a linear mapping in V, all right? This is as simple as that, all right? Now, from the first inequality, what can we say about this linear mapping? Well, what can we say about this linear mapping? So this linear mapping is also about it, right? Because this is smaller than, so if I put this to be a constant C, 0, then this is smaller than V, because VU is fixed. So basically this is bounded and linear form, bounded and linear mapping. All right, so we're gonna continue this on next Monday. All right, so see you next Monday and have a nice weekend. Bye.
I had a question.
Yes. Yes,
It's just about the projects at the end of the semester.
Yes.
Are we not doing those anymore, or
we are still doing it by
what's happening going forward?
So each of you will have like 10 minutes, right? So say we have a class of 50 minutes. So each of you will have 10 minutes, and we do it by this, right? By Zoom meeting. So each of you will present one thing which you find interesting in either the book of leaf loss or the book of resist in 10 minutes. And then so we're gonna need 2 classes for that. Each class will be like for 5 of you, and you're gonna do it like on Zoom, right? So you're gonna present your project for like 8 minutes on Zoom, and I'm gonna give you the grades in front of the class, right? In the sense that you're gonna do it like me. You're gonna present your project say in 8 minutes. And so I'm gonna ask you for like a couple of questions, and then I'm gonna give you a grade, and after, so we need 2 classes, and then so this is how we do it.
Okay.
Is clear?
And so what are the criteria? What are the criteria for our selections? Are they theorems? Are they, I mean,
anything you like, anything you like. If you like an example that which is interesting, you can present it. Say you're gonna have 8 minutes, right? So, and then 2 minutes will be for in front of the whole class. So you're gonna have to spend all of those minutes, and out of, I mean, when you give your presentation, your friends can ask you questions as well. So be prepared for questions from not only from me, but also from your friends. And you also have so you only have 8 minutes. So you try to find something simple, right? Not the proof of Laxman Gram theorem, which is gonna take you like 2 hours, right? So something simple,
okay,
which is suitable for 8 minutes.
Yeah.
And
okay.
all of
and
your friends, yes. Yes.
I was gonna ask, does it have to be in one of our 2 textbooks, or can it be something from, say, functional analysis in general?
Yeah. So my initial idea was from the 2 books, but if you find something interesting outside, but which is helpful for functional analysis, then it's fine. All right. So you can be
Okay.
very creative.
Okay.
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 And do we need to tell you what our project is going to be about beforehand?
No, you don't have to. You can present it in front of the class but try to make it clear, right? So that your friend your friends can understand it and ask questions, right?
Got it. Okay. Okay.
Okay.
Yep. Thanks.
Yes. Any other
All right.
questions?
Have a good weekend.
Have a good weekend. Bye.
Bye. Have a good weekend.
Have a good weekend.